Imagine standing on a piece of land that looks perfectly solid, but beneath your feet, an entire mountain is sliding toward the ocean at the speed of a fingernail growing. This isn't a slow geological era, it's happening right now in Rancho Palos Verdes. For decades, the Portuguese Bend landslide has been a slow-motion disaster, but recently the movement accelerated, threatening to tear apart the very ground the community is built upon. The culprit isn't just gravity, it's a hidden layer of bentonite clay that acts like a slip-and-slide when it gets wet. To stop the mountain, engineers have to remove the one thing making it move: the water. The geology here is a fascinating mess. Millions of years ago, volcanic ash settled into the ocean, forming a layer of bentonite clay that is now buried hundreds of feet deep. When this clay gets saturated with groundwater, its internal friction drops to almost zero. It becomes a lubricating grease for billions of tons of rock sitting on top of it. To solve this, engineers have embarked on a massive $65 million project. They aren't building a wall to hold the mountain back, they're building a system to suck the mountain dry. The plan involves drilling dozens of deep dewatering wells. Think of these as massive steel straws designed to reach the exact depth where the water is trapped. But these aren't your typical water wells. They have to operate in a medium that is constantly shifting, which creates an engineering paradox. How do you build a rigid structure in a moving target? If they can pull enough water out, the friction in the clay layer increases, effectively locking the mountain in place. It's a battle of hydraulics versus geology. By March 2026, the scale of this operation is staggering. We're talking about a network of pumps working 24/7 to move millions of gallons of water away from the slip plane. Every drop of water removed is a victory. But the engineering required to keep these wells operational while the ground is moving is where things get truly clever. The wells have to be incredibly tough, yet flexible enough to survive the immense forces of a moving mountain. It's a delicate balance of material science and mechanical design. But there's a limit to what steel can handle. When you have 1 trillion tons of rock moving in one direction, something has to give, and usually it's the infrastructure. This is the core of the problem. The very wells designed to save the land are being destroyed by the land they are trying to save. It's a race against time. To understand how this happens, we need to look closer at the design of these steel straws and the physics of the shear forces acting upon them. The dewatering wells are marvels of mechanical engineering. At their core is a 12-inch diameter steel riser, perforated at the bottom to allow water to seep in while keeping the silt and clay out. Think of it like a high-tech French press. The steel casing acts as the filter, and a submersible pump at the bottom provides the suction to lift the water 300 feet to the surface. The engineering challenge here is the depth. At 300 feet, the pressure is immense, and any failure in the pump or the casing means a costly and difficult repair. But the real enemy isn't pressure, it's sheer force. The landslide isn't moving as one solid block. Different layers of earth move at different speeds. The most dangerous point is the shear plane, the exact boundary where the moving mountain slides over the stable bedrock below. This is where the physics gets violent. At this interface, the steel casing is subjected to a double shear action. It's like trying to keep a pencil intact while sliding 2 heavy books past each other in opposite directions. To calculate the force at play, engineers look at the shear modulus of the steel versus the driving force of the landslide. 1 trillion tons of moving earth generates millions of foot-pounds of torque. Even the strongest high-carbon steel has a breaking point. When the shear stress exceeds the ultimate tensile strength of the riser, the middle doesn't just bend, it fails catastrophically. In Palos Verdes, these multi-million-dollar steel risers are being snapped like toothpicks. Engineers have found wells that have been offset by several feet in just a few months. When a well snaps, the pump is often lost and the straw is blocked. The water levels begin to rise again and the landslide speeds up. It's a feedback loop that engineers are desperate to break. To combat this, they've tried telescoping designs, casings that can slide and tilt, but even these have their limits when the earth moves this much. The sheer scale of the force is hard to wrap your head around. We are witnessing a battle between human-scale engineering and planetary-scale physics. The engineers are now using sacrificial designs. Instead of trying to build a well that lasts forever, they're building wells that are designed to be replaced every few years. This leads to a fascinating and difficult engineering trade-off. How much do you spend on a piece of infrastructure that you know is going to be destroyed? It's a unique philosophy in civil engineering, where permanent is usually the goal. Here, the only thing permanent is the movement of the mountain.
By early 2026, the strategy in Rancho Palos Verdes has shifted towards dynamic remediation. This means the infrastructure is treated as a consumable resource, much like the fuel in a rocket. The $65 million price tag covers not just the initial build, but the continuous cycle of monitoring, failure, and replacement. It's an expensive way to buy time. But what is the alternative? Without these wells, the rate of movement would increase exponentially, potentially leading to a catastrophic collapse of the entire hillside into the Pacific.
To maximize the life of these wells, engineers have installed fiber optic sensors along the entire length of the casings. These sensors can detect the slightest bend, long before the steel actually snaps. This data is fed into a digital twin of the mountain, a massive computer model that predicts where the next failure will occur. It's like a weather forecast, but for the ground beneath your feet. When the model shows a well is nearing its breaking point, crews can proactively drill a replacement nearby, ensuring the dewatering process is never interrupted. This project is a masterclass in resilient engineering. It acknowledges that we cannot always control nature, so we must design systems that can fail gracefully and be rebuilt quickly. The lessons learned here are already being applied to other landslide-prone areas around the world. From the hills of Italy to the mountains of Japan, the disposable well model is becoming a standard tool. It's a shift from static defense to adaptive management. Instead of a great wall, we are building a great filter. As of March 2026, the movement in some parts of the Portuguese Bend has finally begun to slow. The steel straws are working, even as they break. The community remains on high alert, but for the first time in years, there is a sense of cautious optimism. The engineering trade-offs are paying off. The mountain is still moving, but we are no longer just watching it happen. We are actively managing the physics of the slide, one well at a time. Next time you see a construction crew on a hillside, remember the invisible battle happening hundreds of feet below. It's a world of shear forces, clay lubricants, and sacrificial steel. The engineering behind these dewatering wells is a testament to human ingenuity. We may not be able to stop the earth from moving, but we can certainly change the way it moves. In the end, the moving mountain of Palos Verdes isn't just a disaster. It's a laboratory for the future of how we live on a changing planet.